Okay, the next piece of the puzzle that we're going to put together is looking at a different branch of mathematics or calculus called integral calculus. So we just looked for a second at differential calculus, which has to do more with optimization. And so now we're looking at integral calculus, which is, so in this case, we're going to use this primarily to find the area underneath a curve. And to do that, we're going to need a couple of things. We are going to need our knowledge of limit theory, but we're also going to need this formula or things that are similar to this. So, for example, so we've looked at the parent function of a quadratic a lot. And what we're doing now is we're trying to find underneath this function, this area between the function and the x-axis, how would we find the value of that area? So let's take a look here. So a couple of things that I want you guys to see is one, if we take this area, whatever our bounds are here for this area, so if we take it and we're going to divide this thing into n equal intervals with width 8 h. So get that in your mind that n equals the number of intervals. In this case, each of those intervals is also going to be turned into a rectangle. Now, if you notice, this the right-hand side of this rectangle is going to be the y value, okay, and it's also going to represent the x value. So, so here we are a away from the origin, and we are also that height. So okay, so now let's take the next step. So n is the number of intervals, and the width of each of these intervals is going to be h, which means that if you think about it, then a, which is from the origin all the way across, this a equals the number of intervals times the width of the intervals, which is a equals n times h. Now we're going to rearrange this a little bit. I think this version of it is helpful, but I think there's another version that might be more helpful. So let's take a look at that. So a couple of things that we can do with this is we can rewrite this in terms of h. So h equals a divided by the number of intervals. So in other words, our width, which is h, equals a, which is this total distance, divided by however many intervals we choose. Another thing we're going to look at in just a minute here is we could also rewrite this, and we could say that 1 over n equals h over a. Let me make that look a little more clearly like an h. Okay, so how we're gonna go about this, and what I want you guys to see, the relationship here is pretty important, because what happens here is that as n grows larger, so as n being the number of intervals, as the number of intervals that we choose to divide this thing up by, so as the number of intervals chosen to divide a gets larger, the width of these intervals gets smaller. The width of these intervals gets smaller. Now, why is this even important? Because we're going to use these rectangular strips to represent our area. Now you can see on here, if I have a function that looks like this, you should have seen this earlier as well. So if I choose to take a and I divide it into 3 values, okay, I would end up with something that looks a little bit like this. Now, you can see I have a lot of overage here. So if I'm taking the area, the sum of the area of these rectangles, and use that to represent the value or the area that is underneath here, I'm going to be overestimating by quite a bit. But what happens then is that as I increase the number of times or ways that I split A, so let's say this time instead of splitting it 3 times, let's split it twice that many. Let's split it 6 times. So here's 1, and here's 2, and then here's 3, and 4, and 5, and 6. And what you should find is that I have, if you look at it, so I just eliminated all of this was overage the last time, and I just cut that out. So my estimation of the area under this function just got this much plus this much plus this much closer to the actual value. Now I could keep doing that, but what you're going to see is that as we split A infinitely, the value that we find is going to be closer and closer. It's going to be more and more accurate to the actual value of the area. Now, we can't split it an infinite number of times, but if we could, what would we end up getting? And that's kind of what we're looking at. So let's take a look at the next piece here. So what we do is we're going to take the sum of the areas of all of these rectangles. Well, what is the sum of the rectangles? We said that it's length. It's going to be length. A equals length times width. And we already said that, let's say our width is going to be h, and that is also our x value. So then we want to know what is the height at that point. Well, let's go back to this last piece. So looking at this, let's pick one. So let's go over here. Let's go with R1. So R1, we'll just call this R1. It's not, but, well, yeah, I guess it is. Okay, so R1 is going to be this thing right here. Excuse me, not that thing. The smaller piece is going to be R1. So this piece right here is going to be R1. So our x value here, we are at 2 times h, because here was h plus another h, which is 2h. And then, so that's our x value, and then our y value is the function of that. So the function of 2h, so we're going to take 2h and we're going to plug it in up here to our function, and we're going to get 2h squared as the height. So now let's look back here. So so here we are. So here's our first, so here's R1, our first rectangle, and here's the area of that rectangle. And to find the total area, we're going to sum all of these together. And then our next one is also going to be h, which is our width, times the height, which is 2h, that's our x value, the function of the x value, so we plug that in as 2h squared, and it's going to keep going in the same pattern. So this is 3 h's, that was our x value, because we're at the third rectangle, and we plug it in 3h, okay, and that's going to keep going all the way up here to n times h, or however many we choose. Now what you find when you work all of this stuff out that's really helpful is that there's an h cubed in common. So we work this out. H times h squared gives us h cubed. We're going to have an h cubed here, and all of these different terms all the way through n to infinity. So let's factor that h cubed out. So when we factor that h cubed out, what ends up happening is we just end up with this pattern: 1 squared plus 2 squared plus 3 squared plus 4 squared, etc., all the way up through n squared. Now, why is this even helpful? Why are we talking about it? Well, because what we can do from here is we can replace, we know what h equals. We saw this just a minute ago. We said that h equals, or actually we said a equals the width, which is h, times the number of rectangles. And we rearranged that a little bit, and we said h equals a divided by n. So we're going to substitute in here for h, a over n. Now, the big thing I want you guys to see is all we're doing is we are algebraically manipulating things. And what we're trying to do is we're trying to create a scenario in which we have something that approaches 0. And you'll see this in just a second. So we're looking for a scenario like this, 1 over n. Because as n approaches, so as n gets infinitely larger, then this whole thing approaches 0. You'll see in a second why that's helpful. Okay, so let's take a over n and cube it. So we can work this thing out. This is a cubed over n cubed to begin with. And then we're going to use this formula that we saw, and all this has to do with sequences and series. So we'll use various of these in different situations, using some prior knowledge here. So let's just take this and let's plug in and see what we can figure out. So we have n cubed, and we can cancel out an n, which leaves us with n squared. Now, let's take these n squared and 6, and let's swap places. So we're going to bring this 6 over here, and we're going to now split this. So we brought the 6 over, as we ended up with 6 here, and we ended up with n squared here. So now let's take this n squared and let's split it. We're going to put 1 here and 1 here. Now, take a look at, hopefully I won't lose you here, but let's look at this next step. What did we do? We took this thing and we split it, and we ended up with n over n, which is just 1, and we ended up with 1 plus 1 over n. Here we're going to put an n with this, which means it's going to cancel out, so we're left with just 2 plus 1 plus n. Look at it. So all we did was we put this in with this one, and that gave us simplified to n over n, which is 1. And we put the n with this one. We just split it up. That's all we did. So these two will cancel here, giving us just 2. And this is still over here. This is 2 plus, well, why is this helpful? Because, look at it. After we do some algebraic manipulation to come up with this piece, we're going to find out that as n goes to infinity. Why are we taking n to infinity? Because remember, n is the number of times or the number of ways in which we split a. And remember what we said: if a is split 3 ways, okay, we're going to have a lot of overage here in terms of estimating what our area is that's underneath this function. But the more times we split a, so look at it, the more times, I'll draw it over here. So the more times, remember we went and we split it 6 times. And by splitting it 6 times, we eliminated quite a bit of our overage, which means that when we take the sum of the areas of all of these rectangles, it's going to get closer and closer. The more times we split A, the closer it's going to get to the actual value of the area underneath this function x squared. So this is what we're trying to do. So we're going to try to take n to infinity, as large as it will possibly get. The larger n is, the closer our value is going to be. So what happens here is as n approaches infinity, 1 over n is going to approach 0. Think about it. 1 over 10 is farther away from 0 than if we make n larger. Let's say we make it 1 over 100. 1 over 100, that's 1/10 compared to 1 over 100. So we make n infinitely large, it's going to get closer and closer to 0, which means that this whole thing here is going to, approach 1. Likewise here, this whole thing, as n approaches infinity, this thing is going to approach 2, or 2 plus 0, or 1 plus 0, which leads us to this piece here. Now we can go ahead and work this out. When you work this out, you're going to get 2a cubed over 6, which is going to simplify to a cubed over 3, which is going to be our limit, or the actual area of this space underneath the function y equals x squared.